Welcome to the Deep Dive. Today we're tackling a really foundational subject, something absolutely crucial for anyone dealing with, well, the sheer amount of information out there, database management systems, DBMS.
hmm
Think of this as, building that core knowledge, like prepping for a big test on DBMS. It's essential groundwork, whether you're actually studying or just working with data day to day. Our goal here is to really solidify these core concepts.
Exactly. And our source for this deep dive is DBMS M1.PDF by Sharika TR.
Hmm.
It's a great resource, really focuses on the fundamentals.
Right.
So we're going to walk through, what a database and a DBMS actually are, the architecture behind them, different ways to model data, and the basics of designing databases using the entity relationship model. Basically a solid study session.
Okay, perfect. Let's jump right in. Data, database, DBMS. These terms get thrown around a lot, so let's really try and nail down the definitions. Our source as data is known facts that can be recorded and have implicit meaning.
Right. The raw stuff.
Just the basic facts. And a database is simply the collection of data. Seems easy enough. But the system part, the DBMS, that's a collection of interrelated data and a set of programs to access those data. So it's the software that manages it all.
Precisely. And the key goal here, the main purpose, is to provide a way to store and retrieve database information that is both convenient and efficient. Convenience and efficiency, that's what it's really about.
Like a super organized digital librarian.
Exactly. It's not just storing stuff, but finding it easily, managing huge amounts. The source stresses they're designed to manage large bodies of information.
Which is so relevant now.
Absolutely. And it's not passive storage. It handles both storage of information and mechanisms for manipulation of information. You can work with the data, change it, update it.
And manage it safely, right? Security is a big part.
Huge. The system must ensure the safety of the information stored. Think unauthorized access, data getting corrupted.
Right.
And also, when you have multiple people using it, data are to be shared among several users. The system needs to avoid possible anomalous results. Stop things getting messy when people update things at the same time.
Yeah, we'll definitely need to unpack that concurrency issue later. But first, the source mentions database implicit properties. What are these fundamental traits? The first is universe of discourse, UOD, or mini-world.
Right. So the mini-world concept means a database isn't just random data. It represents some aspects of the real world.
Okay.
Like a university database represents students, courses, enrollments, and crucially, changes to the mini-world affects database. A new student enrolls, the database updates. It mirrors that specific reality.
Got it. A digital reflection of a defined part of the world. What else?
Well, it has to be a logically coherent collection of data with some inherent meaning. The data fits together, it makes sense in context, it's not just a jumble.
Okay.
And finally, it's designed, built, and populated with data for a specific purpose. It has a goal, a reason for existing.
All right. That sets the stage nicely. So moving on to the characteristics of using this database approach. First up is the self-describing nature of a database system. What does that mean exactly?
This is really fundamental. It means the system doesn't just hold the user data, it also contains a complete definition or description of the database structure and constraints.
So it knows its own structure.
Exactly. This description is stored in what's called the DBMS catalog, and the information in that catalog is called metadata.
Metadata, like data about the data.
Precisely. It describes the structure of the primary database. Table names, column names, data types, constraints, it's all documented right there within the system. It's like the database comes with its own instruction manual built in.
That sounds incredibly powerful for managing everything. Okay, next characteristic. Insulation between programs and data abstraction. Sounds like two related ideas.
They are very related. Program data independence means the structure of data files is stored in the DBMS catalog separately from the access programs.
So you can change how the data is physically stored
Right, maybe optimize it.
without rewriting the apps that use it.
Exactly. And program operation independence is similar, but for the actions, the operations.
Mm-hmm.
An operation has an interface, like its name and parameters, and an implementation, the actual code. You can change the code, the implementation, without changing the interface. So again, the applications calling that operation don't need to change. Think of it like updating the engine of a car, implementation, without changing the steering wheel or pedals interface.
Okay. So the application developer doesn't need to worry about the nuts and bolts underneath as long as the interface stays the same. That's huge for flexibility.
It really is. And the source explicitly calls this enabling characteristic data abstraction. Abstraction hides the complexity.
Makes sense. The third characteristic is support of multiple views of the data. This one feels quite intuitive. Different users need different perspectives.
Totally. A database has many users, and each user may require a different perspective or view. Like sales needs customer orders, finance needs billing info, same underlying data, different views.
Right.
And these views can be a subset of the database, just showing specific columns or rows, or they can even contain virtual data that is derived, but is not explicitly stored.
Like calculating a total on the fly.
Exactly,
Yeah.
showing a regional sales total without actually storing that specific number permanently. It's calculated when the view is accessed.
Okay. And the final characteristic listed here is sharing of data and multi-user transaction processing. This brings us back to that complexity of many people using the system at once.
Yes, the concurrency challenge. The DBMS uses concurrency control software to ensure that the result of the updates is correct when multiple users try to change data simultaneously.
You mentioned the ticket booking example earlier.
Right, preventing overselling. And crucial to this are transaction properties, particularly isolation and atomicity.
Okay, let's break those down. Isolation. The source says it ensures that each transaction appears to execute in isolation from other transactions. So even if loads are happening at once, mine feels like it's the only one.
That's the goal. It prevents interference between concurrent transactions. And atomicity. This one's key. Ensures that either all the database operations in a transaction are executed or none are.
The all-or-nothing principle.
Exactly. The classic example is the bank transfer. RS50 from account A to account B.
Right.
Atomicity means both the debit from A and the credit to B must happen successfully if the system crashes halfway through.
Ah, you don't want the money to just vanish.
Precisely. If the credit fails, the debit must be rolled back. The whole transfer is one atomic, indivisible unit. It either fully completes or it doesn't happen at all, leaving the database consistent.
And this ties directly into the concurrent access problems mentioned, like two people withdrawing from the same account.
Absolutely. Without atomicity and isolation, both might read the balance, say RS500, both process a RS100 withdrawal.
And suddenly the account is down RS200, but should only be down RS100 if one went first. Inconsistent.
Exactly. The DBMS concurrency control prevents that mess.
And then, naturally, security problems. Not everyone should see everything. The payroll example is obvious.
Yeah, you need strict controls. HR payroll staff see salaries, but they shouldn't see, customer financial data or vice versa. The DBMS handles authentication, who are you, and authorization, what are you allowed to do.
Okay, so loads of benefits. But let's flip the coin. Advantages and disadvantages of DBMS. The advantages seem pretty clear from what we've discussed.
They are significant. Controlling redundancy, less duplicated data, more consistency, restricting unauthorized access security, efficient query processing, getting info fast, backup and recovery safety net, multiple user interfaces usability, representing complex relationships, modeling reality, enforcing integrity constraints, data accuracy, even permitting inferencing and actions using rules, making the system smarter.
It sounds like a very robust way to manage information. But what are the downsides, the challenges?
Well, there are costs. Cost of hardware and software can be high, especially for big systems. Cost of data conversion if you're moving from an old system.
Right, migration isn't trivial.
Definitely not. Then there's cost of staff training. People need to know how to use and manage it. And, relatedly, appointing technical staff, like DBAs, and of course the risk of database damage hardware fails. Software has bugs, people make mistakes, though good DBMSs have recovery features.
Okay, so it's an investment. Now let's talk about the people involved. Database users and administrators. Makes sense there are different roles.
Absolutely. You've got the users who interact with the data and the admins who manage the system itself. The source breaks users down further into naive users, application programmers, and sophisticated users.
Naive users, that's most people, right? Using apps, websites, interact with the system by using predefined user interfaces.
Exactly. Using banking apps, online stores, social media. They don't need to know anything about the database itself, just the app interface.
Then application programmers are the ones building those interfaces.
Yes, the computer professionals who write application programs. They use tools and programming languages to build the apps that naive users interact with. They need to know how to talk to the DBMS via code.
And sophisticated users. They bypass the standard apps.
Kind of. They interact with the system without writing programs themselves, but they use powerful tools like query languages, SQL is the big one, or data analysis software.
Like data analysts.
Exactly. Analysts, researchers, maybe power business users who need to dig into the data directly and ask specific, complex questions.
Okay. And overseeing all of this is the database administrator, the DBA. Central control over the system.
A critical role. They have a lot of responsibilities, starting with schema definition.
Designing the initial structure using DDL data definition language.
Right. Then defining the storage structure and access method definition, how the data is physically organized for efficiency, setting up indexes, things like that.
Low-level stuff.
Also, schema and physical organization modification, changing things later as needs evolve or to improve performance. And super important, granting of authorization for data access, managing who gets to see and do what, security permissions.
Got it. The source also mentions actors on the scene and workers behind the scene, just a different way to categorize roles.
Yeah, actors are the ones directly involved day-to-day. DBAs, database designers, focusing on the logical structure, end users, and the system analysts, application programmers. Workers behind the scene are more foundational. The people who actually build the DBMS software itself, create tools for it, and maintain the hardware and system.
Okay, helpful distinction. Let's shift gears slightly to talk about the data itself. Structured, semi-structured, and unstructured data. This feels really important today.
It is. The landscape is diverse. Structured data is the traditional stuff, represented in a strict format, nicely organized in tables, rows, columns. Think relational databases, SQL territory, customer records, inventory, financials.
Easy to query and manage.
Relatively, yes.
Yeah.
Then semi-structured data, it does not reside in a relational database, typically, but it does have some organizational properties. Think XML files, JSON. There are tags, hierarchies, some structure, but not the rigid table format.
So easier to analyze than completely raw stuff.
Generally, yes. It's more flexible than structured data. You can often process and store it in relational systems, but it doesn't have to start there. Sensor data, product catalogs might be semi-structured.
And finally, unstructured data, the Wild West.
Pretty much. No predefined format or data model, doesn't fit neatly into rows and columns. Think text documents, PDFs, emails, images, audio, video, social media feeds. It's everywhere now.
And needs different tools to manage and analyze, presumably?
Definitely. Relational databases aren't the best fit. You need different platforms, different techniques for unstructured data.
Okay, good overview. Now let's circle back to how we organize the structured stuff. Data models. What exactly is a data model?
It's essentially a collection of concepts that can be used to describe the structure of a database. So it defines the data types, the relationships between data elements, and any rules or constraints the data must follow.
The blueprint.
Exactly, the blueprint. And most models also define the basic operations. You can perform retrieval, updates, etc.
The source breaks models into categories: high-level or conceptual, low-level or physical, and representational or implementation. Let's start high.
High-level or conceptual models provide concepts that are close to the way many users perceive data. They use intuitive terms like entities, things in the real world, attributes, properties of those things, and relationships, how things connect. The ER model, entity relationship, is the classic example here. Very user-friendly.
Okay. Then low-level.
Low-level or physical models get into the nitty-gritty.
Yeah.
They describe the details of how data is stored in the computer. Think record formats, record orderings, access paths. This is for the specialists, the DVAs, concerned with storage efficiency.
Access paths, like shortcuts.
Sort of. An access path is a structure that makes the search for a particular database records efficient. An index is a common example, helps find data faster.
Got it. And the middle ground, representational models.
Yeah, representational or implementation models bridge the gap. They're understandable by end users, more so than physical models, but not too far removed from the way data is organized within the computer. They hide some storage details, but are directly implementable. The relational model is the prime example here, along with older ones like network and hierarchical, sometimes called record-based models.
So it's like layers of abstraction from user perception down to the disk storage. Now let's clarify. Schemas, instances, and database state. These terms come up a lot.
Right. The database schema is the description of a database. It's the design, the structure tables, columns, relationships, constraints. It's defined during design and doesn't change often.
The blueprint again.
Yes. A schema diagram is just a picture of it. Each part, like a table definition, is a schema construct. The database state or snapshot is the actual data in the database at a specific moment.
So schema is the structure, state is the content.
Perfect analogy. Schema is the empty container design, state is what's inside it right now. And the state changes constantly as data is added, modified, deleted.
But the schema itself can change sometimes. The source mentions schema evolution.
It can. As application requirements change over time, you might need to modify the schema, add a table, alter a column. That's schema evolution.
Okay. Now, putting some of this together, the three-schema architecture. Why three schemas?
It's a standard way to think about database structure, primarily designed to achieve that crucial goal of data independence we mentioned earlier. It separates user views from the physical storage details.
And the three levels are internal, conceptual, and external view. Let's start at the bottom. Internal.
The internal level has the internal schema. This describes the physical storage, how the data is actually laid out on disk, the file organization, the access paths, indexes, uses a physical data model. It's the closest to the hardware.
The actual construction details.
Exactly. Then moving up, you have the conceptual level with the conceptual schema. This describes the structure of the whole database for a community of users.
The big picture view.
Right. It hides the physical storage details and focuses on the entities, attributes, relationships, constraints, the overall logical structure. Usually uses a representational model like the relational model, or sometimes a high-level one. It's the architect's plan of the whole building.
Okay. And the top level, external.
The external or view level has multiple external schemas or user views. Each one describes the part of the database that a particular user group is interested in and hides the rest.
Tailored perspectives.
Precisely. Different users or applications get their own specific window onto the database, showing only what's relevant to them, like individual apartment layouts within the building plan.
So a user interacts with their external view, and the DBMS does the translation work between levels.
Exactly. A request against an external view gets translated by the DBMS to the conceptual level, then down to the internal level to actually fetch or modify the physical data, and the results flow back up, being reformatted for the external view.
That sounds like work for the DBMS.
It is. These translations are called mappings: external to conceptual mapping, conceptual to internal mapping. They take some processing time, but they are essential for
data independence. Let's define that properly now.
Data independence is the capacity to change the schema at one level without having to change the schema at the next higher level. That's the key benefit of the three-schema architecture.
And there are two types, logical and physical.
Yes, logical data independence means you can change the conceptual schema without having to change external schemas or application programs. You could add a new table or attribute at the conceptual level, and existing applications that don't use it are unaffected.
Very useful for exiling systems.
Hugely. And physical data independence is the ability to change the internal schema without having to change the conceptual schema. So you could change how the data is stored physically, maybe use a different file structure, add an index for performance without impacting the logical view that applications see.
So you just update the mapping between the levels.
Exactly. The mapping absorbs the change, insulating the higher level.
Okay, that's a really important concept. Now let's talk about how we actually talk to the database. Database languages and interfaces. We mentioned DDL already.
Right. DDL, data definition language, is for defining schemas. DBAs and designers use it.
What else?
The source mentions SDL, storage definition language, specifically for the internal schema details. VDL, view definition language, for defining those external user views and their mappings. And then the big one for day-to-day use, DML, data manipulation language.
For actually working with the data.
Yes.
Yes.
Retrieving, inserting, deleting, modifying data. DML is how applications and users manipulate the database contents.
And DML comes in flavors too, high level and low level.
It does. High level or non-procedural DML lets you specify what data you want concisely without detailing how to get it. SQL is the prime example. You declare the result you want. Low level or procedural DML requires you to specify the steps, often retrieving data one record at a time. It's typically embedded in programming languages like Java or C++A, and you need loops and code to process sets of records. Think record at a time.
Got it. So different ways to interact via code or commands, but what about user interfaces? Not everyone writes SQL.
Definitely not. DBMS interfaces make databases accessible. We have menu-based interfaces, common on the web, forms-based interfaces, filling in boxes, graphical user interfaces, GUI, using icons, drag and drop, even natural language interfaces that try to understand plain English requests.
Speech input, too.
Yep, speech input and output. And specialized interfaces for parametric users, simplified screens for people doing repetitive tasks, like data entry clerks.
Okay, that covers the core DBMS concepts really well. Now let's dive into that design tool mentioned earlier,
Right.
the ER model basic concepts.
Right, the entity relationship model. It's a high-level conceptual data model, mainly used early in design, for conceptual data design.
Before you pick a specific DBMS.
Often, yes. It helps you understand and structure the information conceptually. It models the world using entities, their attributes, and the relationships between them. And a big plus is its diagrammatic representation, ER diagram, which is relatively easy for non-technical folks to grasp.
A visual blueprint. Let's start with entity.
An entity is a basic thing or object in the real world that we want to store information about. It can be tangible, like a student or car, or intangible, like a course or account. It needs to be distinguishable.
And an entity type.
That's a classification. A collection of entities having similar attributes, like student is the entity type, represented by a rectangle in the ER diagram.
And the entity set is just all the actual student instances.
Exactly. The collection of all entities of a particular type currently in the database. Type is the template, set is the collection of instances.
Okay. Entities have attributes, they're properties.
Right, properties. That basically describes it. For an employee entity, employee name, salary, each attribute has a domain, the set of allowed values, like integer, text, date, represented by ovals connected to the entity rectangle.
And attributes themselves have different types. First, simple versus composite.
Simple attributes can't be broken down further, like salary. Composite attributes can be subdivided. The classic example is name being composed of first name, middle name, last name, or address into street, city, zip.
Make sense? Then single-valued versus multi-valued.
Single-valued means an entity instance can only have one value for that attribute, like date of birth. Multi-valued means it can take more than one value, like phone number. Someone might have several. Multi-valued attributes often get a double oval in diagrams.
Okay. Stored versus derived.
Stored attributes are just that their values are stored directly, like birth date. Derived attributes have values that can be determined from other attributes, like age can be calculated from birth date and the current date. You might not need to store age explicitly. Derived ones often have a dashed oval.
Interesting. And complex attribute, a mix.
Yep, combination of composite and multi-valued. The source gives address phone as an example, where you might have multiple phone numbers associated with potentially multiple addresses, which themselves are composite. Requires special notation sometimes.
Okay, null-valued attributes. This means empty.
Not quite empty, more like value unknown or not applicable. It's distinct from zero or a blank string. If someone doesn't have a middle name, that attribute might be null.
Got it. And super important, key attribute.
Crucial. A key attribute, or a set of attributes working together, has a unique value for each entity and therefore uniquely identifies every entity in the entity set. It can't be null.
Like a student ID number.
Exactly. Enrollment or enrollment no in the source example. An entity type might have several potential keys, candidate keys, and one is chosen as the primary key. Key attributes are usually underlined in ER diagrams.
In domain, we mentioned just the allowed values like grade, A, B, C, F.
Right. Now, entities don't live alone, they connect. That's where relationships come in. A relationship relates two or more distinct entities with a specific meaning, like employee works on project.
So we have the relationship type, set, and instances.
Yes. Relationship type is the general association, like works on, between employee and project. Relationship set is all the specific works on links currently existing. A relationship instance is one specific link. Employee X works on project Y, represented by a diamond connecting the entities.
And relationships have rules or constraints, mapping cardinalities and participation constraints. Before those, what's the degree of a relationship?
Simple. The number of entity types participating. Degree 1 is unary, rare, like employee supervises employee. Degree 2 is binary, most common, employee works in department. Degree 3 is ternary, teacher teaches student in course. Each relationship has a name, a degree, and cardinality.
Let's focus on cardinality ratio for binary ones. That's about the numbers.
Yes, the maximum number of relationship instances an entity can participate in. How many of one entity can relate to how many of another? 4 main types.
1-to-1, 1.1.
Like in some systems, one manager manages one department, and one department is managed by one manager. At most, one on each side.
1-to-many, 1N.
One department can have many employees, but each employee belongs to only one department. One side can link to many, the other side links to at most one.
Many to one, N1.
Just the reverse. Many employees work in one department.
And many to many, MN.
Many students can enroll in many courses, And one course can have many students, many allowed on both sides. Diagrams use lines and symbols like crow's feet to show these ratios.
Okay. And the other constraint, participation constraints.
This tells us if an entity must participate in the relationship. Minimum participation. Total participation means every entity of that type must be in at least one relationship instance, shown with a double line. Example, maybe every loan must have a customer, borrower.
So a loan can't exist without a borrower.
Right. Partial participation means it's optional. Some entities might not participate, shown with a single line. Example, maybe not every customer has a loan. So customer participation in borrower is partial.
Can you specify numbers too?
Yes, you often see min-max notation, like an employee must work for exactly one department, 11.1, and a department must have at least 5 employees, but no more than 100, 500. Specifies both minimum and maximum participation.
Okay, clear. Now, types of entity types, strong versus weak.
A strong entity type is the normal kind. It has its own primary key. Its existence doesn't depend on another entity type. Single rectangle in diagrams.
Like employee or department.
Exactly. A weak entity type doesn't have its own full primary key. Its existence depends on another identifying or owner strong entity. It has a partial key, discriminator, that only makes it unique within the context of its owner. The source uses professor strong with professor ID and professor dependence, weak. A dependent only makes sense in relation to a specific professor. The dependent's name might be the partial key unique for that professor's dependence, but maybe not unique across all dependents. Weak entities get double rectangles, and the identifying relationship gets a double diamond.
Got it. Dependent existence. Finally, relationship of degree 3, ternary relationship, involving 3 entities.
Right, like the source example. Supplier, part, mobile, linked by a SUPPLY relationship. Supplier supplies a part for a mobile model. Cardinality here is trickier. You have to ask questions like, for a given supplier and part, how many mobiles can they supply it for? One or many. For a given mobile and part, how many suppliers can provide it? You check constraints across pairs relative to the third.
A bit more complex to analyze.
Definitely. The source then shows practical ER diagrams, car insurance, hospital, university, student marks. Seeing these concepts applied really helps cement understanding.
Absolutely. It shows how you'd actually model these real-world scenarios.
Yeah, taking the theory and putting it into a practical design structure.
Well, that was certainly a comprehensive run-through of these foundational DBMS concepts and the ER model basics. Feels like we've covered the core material someone would need for, say, that first big test on the subject.
We really have. We defined the core terms, data, database, DBMS. Explored key characteristics like the self-describing nature and data abstraction. Looked at the Three-Schema Architecture and its role in data independence. Discussed users, admins, the different types of data, and then got into the nuts and bolts of the ER model, entities, attributes, relationships, constraints. It's a solid foundation.
It definitely is. Understanding these building blocks is just so crucial for anyone working with data today, whether you're building systems, analyzing information, or even just using complex applications.
Absolutely. And maybe a final thought for our listeners. Think about a system you use every day. Social media, online banking, a streaming service. It definitely relies on a database. How might concepts like different user views or data independence be working behind the scenes to give you your specific experience while serving millions of others? What kind of data, structured, unstructured, do you think they're managing? It makes you appreciate the complexity humming away underneath these smooth interfaces.